All right, everybody, it's Mr. Reboff. This is our AP Stat summer work. We're going to get two chapters out of the way. That'll give us more time to kind of spread things out, a little bit less homework, no work over the breaks, right? All that good stuff. So hopefully this is something that will pay off. It should be sweet or short and sweet, quick, sweet. Here we go. Quit talking, Mr. Reboff. Let's go. All right, so we were talking about probability. Sometimes probability and statistics is the name of the class. In general, the probability of an event happening. Okay, that's what this means. This is the probability of event A. Whatever we define A is. A could be I make a free throw, probability of Mr. Rebuff making a free throw, probability of coin landing heads, right? Could be anything, right? Um, Probability in general is the number of successful outcomes, whatever you define as being a success, over the number of total outcomes. Out. Spelling is hard. There we go. So the number of successful over the number of total, right? So if I have a fair coin, right, and I say a head is a success, I would have one successful outcome possible, and I would have two total outcomes, head or tail, right? So the probability of a head is 1/2, right? Right. So sometimes you'll see it written as this: successes over successes plus failures, right? So you'll see that probability of anything. We're going to be dealing with probabilities all year long. Okay, huge part of AP Stat, right? Probability has to be between 0 and 1. Okay, 0 means it's impossible, 1 means it is certain. Okay, impossible, there's a 0% of something happening, and 1 is certain. You could look at this as percentages as well. This is 0 to 100%. All right, the law of large numbers, right? Things are in general not predictable in the short run unless they're 0 or 1. So not predictable in the short run, but can be predictable in the long run. Okay, I know if I flip a single coin, I don't know if it's going to be heads or tails. If I flip 5 coins, I don't know what's going to happen. If I flip 1,000,000 coins, I know that about 500,000 of them will land heads and about 500,000 will land tails. It'll never be I won't say never. It's unlikely that it'll be exactly 500,000 of each. But when we run the averages of each or the percentages of each, it's going to be really close to 50%. Okay, I know that in the long run, right? We get that. All right. Simulations using the table of random digits. And that's what we're going to do here. We're going to simulate a situation using these random digits here. There's entire books of random digits. You can go find web pages of just random digits out there, and they help us simulate things. Okay. Sometimes that's the best way to figure out the probability of something happening because it can be pretty compound. So when we do this, we do Dursk. Dursk. I don't know if this one's going to catch on. We have a lot of things in this class. I'm going to try to get Dursk going this year. So what are we doing with the digits? How many do we use at a time? So how many at a time? And what do they represent? What do they rep? All right. Are we ignoring any? Are there any numbers we ignore? Sometimes there are, sometimes there's not. We'll do an example of each. Okay. Are repeats okay or not? Sometimes they are. Are repeats okay? It depends on the situation, right? You have to think about the situation. Is the probability staying the same? Is it not? Stop, obviously, when to stop. When to stop. And then count. What are we counting? What are we counting up? And this is usually from the question itself. Okay, so this is from the question. When they ask the question, usually these are straight from there. We can use the context of the problem. All right, so here we go. A weighted coin, an unfair coin. A coin is known to be biased in such a way that the probability of getting a head is 0.4. So I'm going to write that down somewhere. Probability of a head, just so I can see it, is equal to 0.4. 40% chance. How many flips would it take on average to get 5 heads? Design and carry out 4 trial simulations given the following random digit table to help answer the question. All right, so we have to use this now. The way on the AP, and about once every like 4 or 5 years, there's a question kind of similar to this where you have to use this. We have to go through these things. Okay, all of these are important things. So let's do it. Let's do digits. Digits, if it's a 40% chance of getting ahead, I might do something like 0, 1, 2, and 3 count as heads. And then 4, 5, 6, 7, 8, and 9, that's 1, 2, 3, 4, 5, 6, count as tails. Okay, I'm going to use one digit at a time there. So one digit at a time. There we go. So that's how I'm using the digits. I've labeled what they mean, and I'm doing one digit at a time. All right, we're going to ignore any. Nope. Ignore none, right? Because we're using 0 through 9. We're using all 10 digits. Ignore nothing. All right, how about repeats? Are repeats okay? Repeats are actually okay. If I throw out repeats, like if I say, okay, 1 is ahead, I can't use a 1 again. Now I only have if I throw out the 1, I have a 3 and 9 chance of getting aheads, and it needs to stay 40% each time. That coin doesn't know that it was flipped heads, and now it should be tails more often. Coins don't work like that. So repeats are okay. We want to keep the 40% staying at 40%. So repeats are okay. Let's see, what's next? Dursk. Let's see, when do we stop? Stop when, how many flips on average to get 5 heads? So stop once we have 5 heads. And then what am I counting? It says design a carryout to give the following digits to help answer this question. How many flips it takes to get 5 heads? Count how many flips. Cool. So there we go. These are my instructions. On the AP, when they grade your work, they think in the back of their heads, if I gave your instructions to 5 different students, would they do the exact same thing here? And if they would all do the exact same thing by following your directions, then you did a good job. Okay, so let's do it. Ready? Go. So we got a head, and then we got a tail, a tail, a tail. 2 is heads, 4 is tails, tails, tails. We have a head. We have a head. How many heads is that so far? 1, 2, 3, 4. We have a tail, a tail, a tail, and a head. And I stop the first trial right there. So it says design and carry out 4 trials. There's 1. And how many heads do we have? 1, 2, 3, 4, 5. How many flips did it take? 4, 8, 12, 14. So it took 14 flips the first time. Okay. Sometimes you'll do this like trial 1, 14 flips. I'll just put that over there, right? And then we'll do trial 2, trial 3, trial 4. We'll do the next one, then we'll stop. You could do the others if you want. So we have a head, a tail, a head, a tail, a tail, a tail, a tail, a head, a head, a head. All right, 3, 1, 3. Is that 5 now? 1, 2, 3, 4, 5. Good. We stop there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Trial 2 was 10 flips, right? So we keep doing that, okay, showing our work and getting the third and the fourth. If you want to practice, go ahead. That'd be an extra way to do it. Cool, cool. All right, so let's jump into more of an AP style question. The first one's kind of easy. This one's going to be more typical right here. Looking at hiring discrimination. An airline just finished training 50 pilots, 30 were male, 20 were female to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers announced they will use a lottery to determine which pilots filled the available positions using the put everyone's name in a hat method. So they're going to put all 50 of these people's name in a hat and just pull out 8, and those are the people, right? Of the 8 captains that were chosen with that method, 5 ended up being female and 3 are male. Some of the male pilots are like, oh, this isn't fair. So I don't know, they're threatening a lawsuit, right? So was the lottery fair? Design and carry out a simulation using a table of random digits below. Be sure to explain your methodology and repeat the simulation 5 times. Okay, so we're going to DIRSC it, DIRSC. Digits, how many am I using at a time? Well, think about it. We've got 50 pilots. I've got to use 2 digits at a time, right? So 2 digits at a time. 30 are male. So I'm going to go 1 to 30 represents male. But if I'm using 2 digits at a time, I can't use 1, right? Because let's say I get to this 1 here. Does that mean 1 or does it mean 12, right? Does this mean 2 or does this mean 23, right? So I have to keep everything in 2 digits, right? So 2 digits, 2 digits. So 01 to 30 is male, and that means 31 to 50 is female. What are we ignoring? Well, we are going to ignore, sorry, I should write ignore. We're going to ignore 00. That's the one that people forget a lot. And then we're going to ignore 51 to 99. Okay, so those are digits we're going to ignore. Are repeats okay? No, no repeats. No repeats. Why? Because we're choosing 8 pilots, right? We can't have Jimmy Souza pick twice, right? He can't be 2 of the 8 pilots. He can only be 1 of the 8. So what did I wrote? No repilot. I was thinking about the word pilot. No repeats. Mr. Rebuff. No repeats. So repeats are not allowed. All right, when do we stop? Stop when we have 8 pilots, right? We can use the context of the problem. That's perfectly fine. And what are we counting? We're going to count number of male and female. Okay, we're just going to see how weird is it that it was 5 and 3, given that it was like 40% female, 60% male in the population. I'm concerned that there are only 30 males in the training. Like why is that not more even? All right, here we go. Let's do it. Ready, ready, ready? Here we go. So here's how I do it. I underline 2 at a time. Okay, so I'm just going to underline a whole bunch of them, 2 at a time, 2 at a time. Notice we're going to have a bridge because there's 5 in each, and that's okay, right? So 2 here, the 4 and the 4 bridge, 2 here, 2 here. Maybe that's enough. Let's find out. Okay, so 38, that is female. 71 is an ignore. 23 is male. 15 is male. 12 is male. Let's see, 1, 2, 3, 4 so far. 8 is male, 58 is ignored, 86 is ignored, 14 is male, 90 is ignored, 72 is ignored, 29 is male, 1, 2, 3, 4, 5, 6, 7. We have room for one more. 44 is female, so we will stop there. I put a line to stop. And trial 1, we have 2 females and 6 males. All right. All right, all right. Let's do trial 2. We can either keep going from where we left off, or we can go to a new line. Notice they provide 5. I'm going to go to a new line. Why not? So 58, 72, those are going to be ignored. 20, 36, ignore. 19, 18, 66 is ignored. 96 is ignored. 2. Let's see, 34, 62 is gone. 57's gone, 59's gone, 58's gone, 56, 86, 91. Oh my gosh, 79. All right, doubles or 07. Where are we at so far? We've got 1, 2, 3, 4, 5, 6, 7. 81 is ignored, 86 is ignored, 71 is ignored, 15 finally. All right, so here we go. 22 is male. 20 is male, 36 is female. 19 male, 18 male, 2 male, 34 female, 7 male, 15 is male. Let's see, is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Again, we've got 6 male and 2 female. Let's trial 2, right? Let's do one more. I mean, you can keep going and then we could kind of answer the question. I guess was a lottery fair. We may need to go a little bit more. Trial 2, trial 3. 26 male, 18 male, 86 skip. Skip, 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 female, male, skip, skip, male, female, 77, skip, male, skip, 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 06, male, 68, skip, male, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I didn't need that last one. This time I have 3 females. One, oh no, I have 2 again. 1, 2. 1, 2, 3, 4, 5, 6. Wow, 6 and 2 again. All right. If you want to fast forward through this, that's totally fine. We're going to get through all of these. I'm going to pause and come back when I've done it. All right, here we go. I've finished these two. I ended with 1, 2, 3, 4, and 4 in this one. So trial 3, trial 4, trial 5. 4 was 5 and, oh, sorry. Say 5 and 5. I think it's 4 and 4, right? 1, 2, 3, 4. 4 males, 4 females, and then trial 5 ended up being 1, 2, 3, 4, 5, and 3. 5 males and 3 females. And now I could answer the question, right? I'd say that out of 5 times, not once did we have 5 female and 3 male. It seems like it might be rare, right? It didn't happen once in 5 times. That doesn't mean a whole lot because this is a pretty small sample size. Okie dokes. All right. So that's it. The rest is up to you. This is additional practice. Some people like to wait as they prepare for an exam or something like that and come back and do these. What I'll do is I will put the answers here for you so you can see it. And yeah, cool. All right, so do as you want. You could bounce here. If you want to watch and do these, if you want to try it and then look at it, if you want to save it for later, do that. That's fine. Up to you. All right, so additional practice. Men and women are about equally likely to earn degrees at City University. However, there's a question whether or not women have equal access to the prestigious School of Law. This year, only 4 of the 12 new students are female. Using random digits below, carry out 5 trials simulation that could be used to estimate the probability of 4 or fewer females in a group of 12 randomly selected students. It says we're going to carry out 5 trials. Oh my gosh. I think there actually is enough room for that. All right. So you're going to come up with the DERSC. So come up with a DERSC. And then we're going to carry it out. Cool. All right. So I would do 1 digit at a time. Where 0 to 4 are male and 5 to 9 are female. That's 5 numbers, and this is 5 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's fair. That's 50-50. It's weird sometimes when you go 0 to 4. You're like, shouldn't it be 0 to 5? No, it's 0 to 4 because that's 5 digits. Are we ignoring repeats? No, repeats are okay. I think there's just a large enough group of people that, taking a sample of 12 students is not a big deal. So repeats are okay. Ignore nothing. Ignore none. We really don't have to say that because, 1 digit at a time and we're naming all the digits. So repeats are okay. When are we going to stop? Stop after 12 students. They're not really students, they're numbers, but they represent students, so that's fine. We're putting in context. And then we're going to go find the probability that we're going to have 4 or less female students. Okay, so there we go. I've described how I'm going to use it. If somebody used what I did here, they're going to get the exact same thing, unless I make a small mistake or something, right? All right, so these are groups of 5, 5, 10, 12. 3, 8, 9, 10, 11, 12. Let's see, 1, 6, 7, 8, 9, 10. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12. 1, 2, 3, 4, 9, 10, 11, 12. 1, 2, 7, 8, 9, 10, 11, 12. All right, there we go. So there's my 5 trials. 1, 2, 3, 4, 5. 12 are in each, and 0 to 4 are male. So I'm just going to count the number that are 0 to 4. This is male. 1, 2, 3, 4. So 4 male, 6 female. Oh, sorry, this is out of 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 12. Oh, dang. Okay, sorry. If there's 4 male, there's 8 female. Okay, so 4 male, 8 female. Um, let's see, here we go. Out of these 12, male, we'll keep going male. Male, 1, 2, 3, 4, 5, 6, 7. 7 male, 5 female. Here we've got 1, 2, 3, 4, 5, 6, 7. 7 male, 5 female. Here we've got, let's see, 1, 2, 3, 4, 5. 5 male, 7 female, I think. Right? I think so. Here we got 1, 2, 3, 4, 5, 6, 7, 8. 8 male, 4 female. Here we've got, oh, that's it, right? So how many times did we get 4 or fewer females? It didn't happen, right? Um, we have 5 females here, 5 females here. Oh, did we have 8 and 4 here? Let me double check. 1, 2, 3, 4, 5, 6, 7. Oops, no, it should be 7. My bad. Some of you are yelling at the screen like, Mr. Rebuff, you counted wrong. 7 and 5, right? We got 7 and 5 3 times. So would it surprise me if every once in a while we got 4 out of 12? No, it's not out of the realm of probabilities, but we got 0. So you would make some comment on this. Based on my 5 trials, what is the estimated probability? Probability of 4 or less via my simulation is 0 out of 5. People, that's it, right? So probably 4 or less happening via my simulation. Sorry about my writing, it got really bad there. Is 0 out of 5, right? So via my simulation, there's a 0% chance. If I actually conducted this simulation 20, 30, 40, 100 times, that might give me a closer idea, right? So law of large numbers kind of takes over the more trials you do as well. So that's that. All right, people, we'll see you. Bye.